Okay, in this next video, we are going to cover the math underlying what are phasors and how they connect to sinusoidal steady-state signals. So first, a word about what is different about this new AC or sinusoidal section compared to DC signals where we had simply transient pulses. And if we consider the notion of transient signals that we've been considering up until this point, we're envisioning, a digital signal that might consist of a train of pulses or a train of rise and falls from 1 to 0 or 0 to 1. This can be some arbitrary pattern here, and it could look like this. And these, high voltage, low voltage are a sort of digital representation of some signal that's being sent. And let's say I ask you the question, I define this as point A, and I define this as point B. And I tell you that the voltage at point A is high, it's 5 volts. And then I ask you the question, what's the voltage at B? Let's say you didn't see the black line, all you saw was a knowledge of what's at point A and the knowledge that this is a digital signal. The knowledge of what the voltage is at point A tells you nothing about what the voltage is at point B, because there's all these flips that could or could not happen in between, so you really have no way to know whether it ends up as a 1 or a 0. So for this reason, there's essentially no time correlation, no autocorrelation on this signal beyond, 1 clock cycle or so. And there's no way to know what the voltage is at B if you know what the voltage is at A. And so for that reason, we have to sort of consider each of these features to the digital sequence separately, right? This is a rise, and this is a fall. And if we know how the transmission line responds to a rise and how it responds to a fall, then the complete digital signal is really just a sum of all of those responses with proper delays thrown in. All right, so that's a DC signal. In the case of a sinusoidally varying signal, though, we're dealing with something that looks like this. All right, there's a sinusoidal variation to it. And if you know what the frequency is, and let's say that frequency is F, and we've all agreed on what that frequency is, which is very common in RF or in AC or in sinusoidal applications. If we agree what that frequency is in advance, you're also defining the wavelength, right? The wavelength being the distance between consecutive peaks or distance with consecutive nulls, or the repetition length, right? So this wavelength we're going to call lambda. There's a very clear relationship between the frequency and the wavelength, which if you multiply them gives you the propagation velocity. This one is absolutely worth memorizing if you don't already recognize that from earlier courses. But now let me ask you the same question, right? If I tell you what the voltage is at point A, and I ask you what's the voltage at point B, now you know the answer, right? Or you have a pretty good idea. In this case, as I've drawn it, point A and point B are approximately a wavelength apart. And so then you can say, well, A and B must have the same voltage, right? That's not information that we had before, but it is information now because we know that the shape of the voltage as a function of distance follows this repetitive pattern every lambda meters, right? And I can even say, let's say there's a point C right here, which is halfway in between. And let's say point C is a half a wavelength away. So we know that the voltage at point A equals the voltage at point B. We also can say that the voltage at point C is a negative of the voltage at point A, because at a half a wavelength, you're always on the flip side of the sine wave, right? So, and this is always going to be the case if you have this sort of sinusoidal steady state with a defined wavelength, right? So for this reason, unlike the transient case, what we've got is a clear definition of what the voltage is at point A as a function of what it is any other place in space, right? And so using that information, there's a lot more that we can say about the evolution of voltages and currents on a transmission line. Again, be constrained by the wavelength being a fixed number. All right. Now, when we're dealing with wavelengths, or when we're dealing with sinusoidal signals, the general signal that we might deal with would look like this, right? V as a function of zt equals V in the positive direction times cosine of 2 pi ft plus phi. And this would be, let me just make this more generic. Let's not even worry about a wave just yet. Let's just have a generic sinusoid, a generic sinusoid. All right, so we're just going to say this is f as a function of x. Will in general be some scalar multiple a times a cosine of 2 pi f times t plus some phase factor phi. The phase factor is going to slide our cosine to the left or to the right. And just to remind you, the sine is already part of this because sine of x equals the cosine of pi over 2 minus x, where pi over 2 is in radians. Okay, so if we see a sine here, we can always convert it to cosine. We're gonna stick with cosine as a convention. Okay. Now, if we take a look at this and examine it, we've already agreed together on what the frequency is, right? We know what's a gigahertz or 2 gigahertz or 300 megahertz. We know what the frequency is, so we don't need to bother writing this every time. The only new information here is the amplitude and the phase. If I give you those two numbers, you now know exactly what this function is. So we can throw that away and replace f with what's called a phasor, right? And so to denote a phasor, I'm going to write f, and I'm going to put a little squiggly line over it to indicate that it's a phasor, right? And what I'm going to do is I'm going to write down the amplitude, a, and then I'm going to do an exponent, e to the j times that phase phi, right? Where j equals the square root of -1. All right, it's what we call an imaginary number. So if I take the amplitude and phase and I plug it in here, then this is a way of capturing all the information that we need, the amplitude and the phase. And we can convert this back into the time domain form with the following trick, right? F of t is going to be the phasor value times e to the j omega t, and then we're going to take the real part of that, right? That basically allows us to take the phasor value and convert it back into the time domain. We'll see why that's the case in a second. All right. So here we got a compact number that tells us everything about the sine wave, but it's really only one number, right? This is going to have a real part, a, and an imaginary part, j times b. Right, this is a little a. And so how do we go back and forth between this real and imaginary part and this amplitude phase? So for that, we're going to write the following. It turns out if you do a Taylor series expansion on e to the j phi, it works out to be cosine of phi, sorry, that's phi, not theta, cosine of phi plus j times sine of phi. You can verify this with Taylor expansion. We're not going to do this in this course. But what this tells us is that we can represent this graphically with a real and imaginary axis with a 1 on the horizontal axis, a j on the vertical axis, in which case e to the j phi is going to have length 1, and it's going to have an angle phi with respect to the horizontal axis. So if this is what we're going to call a phasor, almost drawn as a vector, and this has length 1, then this angle right here is going to be phi. the angle counterclockwise from the horizontal axis. If we represent it in that form, then the projection of that vector onto the horizontal axis is the real part A, and the projection of this onto the vertical axis is little b, the imaginary part. And so we can represent the same phasor as an a e to the j phi, or we can represent it as a plus jb as a real imaginary part. And you can convert back and forth just by applying geometry to this phasor using this two-dimensional diagram. All right, and one of the things this helps us do is it helps us do mathematical operations on sinusoids very quickly. All right, I'll give you a quick example. All right, let's say I ask you the following question. All right, let's say I ask you to figure out what is cosine of omega t plus pi over 4 plus cosine of omega t plus 3 pi over 4. I ask you to figure that out. That's not something you can do in your head. It's not something you can do in a straightforward fashion, but phasors actually make it very easy to do this, because what we're going to do is we're going to convert each of these into a phasor, right? This cosine right here has an amplitude of 1, right? You can put a 1 right here, right? So it has an amplitude of 1, and then I'm going to write down e to the j, and the phase right here is going to be this pi over 2. It's going to jump down into that exponent, right? So this is going to be a j times pi over 2. Very important, everything is in radians at this point, right? We're sticking with radians. And remember that pi radians equals 180 degrees. Right? Now this number, e to the j pi over 2, is something you can directly evaluate. You can put it into a calculator, you can put it into MATLAB, and you'll get an answer. Sorry, I wrote a 2, that's actually a 4. Let me just erase that. All right, let's do the same thing with the other term here. This again has an amplitude of 1, and it's going to be an e to the j. We're just going to write down what the phase is, and it's 3 pi over 4. Okay. Let's look at this graphically. All right, so for the first one, I'm going to draw a vector here in this real imaginary axis, the complex plane as it's sometimes called. And it's going to have length 1, it's going to have an angle of pi over 4 with respect to the x-axis. That's 45 degrees. Right, so the first term is going to be right here. Right, that first one's going to come over here. The second one is, again, has length 1, but it has an angle of 3 pi over 4, which is 135 degrees. So that's going to go over here. All right, so this one is represented over here. All right, now we're just adding these up. And so you can take the projections of each of these, and you can see pretty quickly that the projections onto the x-axis are equal and opposite, so they're going to cancel. Right, this is a 1 over square root of 2, and this is 1 over square root of 2, and they're going to cancel out, right, if we add the 2 up. The vertical component of these are the same. It's 1 over square root of 2. Right? This angle is 45 degrees. And so these are going to add up. And so the result of this is going to be a single vector that is straight upwards in the direction of j, and it has intensity of 2 divided by the square root of 2. Now that we've got this in phasor form, we can convert it back into time domain. So this is going to have amplitude of 2 over square root of 2. So here it is in the phasor domain. Now let's convert it back into the time domain. And I'm going to write down the amplitude first. It's 2 over the square root of 2. And there's a j right here because this 2 over square root of 2 is in the direction of j. And so the j basically means that there's a 90-degree phase shift to it. So I'm just going to write down a cosine of omega t plus pi over 2. And here we go. There's our answer. You can verify this if you'd like with MATLAB with a graphing calculator, but using phasors, we've actually figured out how to sum up these cosines together. All right, so the idea here is that phasor lets us keep track of adding and subtracting and multiplying and dividing phasors without having to bother keeping track of the entire time evolution. The phasor itself represents everything. We know how to convert back and forth to the time domain form, and that's going to greatly simplify the material that we're going to do. All right, I want to say one more thing, which is just expand a little bit on why this real part of phasor times e to the j omega t works well. And I'm going to say what e to the j omega t is. E to the j omega t is a vector that has length 1. Right, so we're going to bring this over here. It has length 1, and at t equals 0, it has an angle of 0 degrees. All right, so this is t equals 0. And then as t increases, the phase factor is omega t, it's phi. So the phase with respect to the horizontal axis is increasing linearly with time. So at t equals some positive number, it'll be here, right? T equals 0 positive. So this vector is rotating like that. All right, so when we multiply by e to the j omega t, what we're basically doing is we're taking our phasor vector and we're spinning it around in a circle. Right? The phasor tells us where we start out at t equals 0, and the e to the j omega t makes it start spinning in a counterclockwise direction. As it's doing that, we're taking the projection onto the horizontal axis, and we're taking the real part. And that's going to swing back and forth from left to right and give us a sinusoidal variation. All right, I'm going to show you a video that kind of describes this. All right, so the blue line represents our phasor, right? That's the phasor value. And when we multiply it by e to the j omega t, we're going to force it to start rotating in the clockwise, in the counterclockwise direction. As we're doing that, the projection onto the real axis is going to be plotted on the bottom plot here as a function of time as we rotate that phasor around. So I'll play this video and you can take a look. You'll see the dashed line that'll appear on the top as this starts to rotate. So the dashed line is the original phasor value, and the solid blue line on the top is as we multiply by e to the j omega t as we increase t. Right, and as we do that, we're mapping out the real part of that, or the projection onto the real part is what's shown in the bottom plot. And it's a sine wave. The amplitude of that sine wave is directly connected to the length of that initial phasor. And the phase of this sine wave on the bottom is connected to where you are, where that blue line starts in terms of like where it is in the circle, where it is in the clock. All right, I'll play this one more time so you can see it. All right, so that's how we can convert back and forth from the phasor domain into the time domain with this funky e to the j omega t in there and the real part. All right. So that concludes this video. In the next video, we'll talk about how we can use phasors to better describe a propagating wave, in particular along a transmission line.